Hi everyone, my name is Oliveira and I'm going to present our work about using a VR field studies to assess the effects of visual and haptic cues in the wild locomotion. Walking involves balance and coordination of muscles, so any deviation from this is considered a gait disorder. These disorders have various causes such as age, strokes, Parkinson's disease. Our work was primarily motivated by Parkinson's disease because as this disease progresses, many are the effects in patients' ability to walk, as it can be seen in that video. There is no cure or treatment that completely addresses the effects of Parkinson's disease on gait. However, these symptoms can be minimized through cueing. There are three major forms of cueing: visual, auditory, and haptic. Visual and auditory cues are the most used and studied types of cues. However, gait normalization had been shown while using the three types of cues. And although many studies have demonstrated the effects on patients' gait inside the lab, very few studies demonstrate the effects out in the wild. In fact, we may say that visual and auditory cues are hard to produce outside the lab, and are likely to lead to a cognitive overload and distractors, whereas haptic cues are proven to be less cognitively taxing. Therefore, our work will focus particularly on haptic cues. The main objective of our study is to understand the effects of various stimuli on patients' gait, attention, and safety, especially when used outside the lab. In order to do that, we had used a VR street with three different distractors: a car, a pedestrian, and a crossing light. During the simulation, we will be measuring gait parameters such as cadence, step length, and velocity. We are also going to be measuring gait parameters such as the hits and the dwell time at the distractors, and usability parameters through a SUS and a preference questionnaire. So now, what are the stimuli that we used? A classic approach is to use visual cues. These are bright traverse bars on the floor. In our study, the distance between the bars is equal to 150% of the step length measured during baseline walk. Another classic approach is haptic one pattern, one watch, which is represented by a single vibration on a wrist, only giving the participant temporal information. In our study, the cadence of the vibrations matched the cadence from the baseline. A novel approach is haptic one pattern, two watches, represented by a simple vibration played alternatively on the right and left wrist, indicating to the participant how to map the vibration with the correspondent foot. The last stimulus used was haptic two patterns, one watch, represented by two vibrations patterns on one wrist, being each vibration patterns mapped with a foot. Once again, it is important to refer that our main objective concerning gait is to improve it. This means less but longer steps. Therefore, we aim to get an increase on step length and velocity but a decrease on cadence. And despite the fact that all our participants did not have any gait disorder, their gait seemed to suffer an improvement during haptic cues. For example, regarding the step length during visual cues, it was noticed a great reduced in contrast to an increase during haptic cues. Cadence was improved in all cues, however, greater improvements were noticed during haptic cues. Regarding gait results, as expected, visual cues had significantly lower numbers of hits and dwell time, meaning that when submitted to this, participants seemed to not be aware of the distractors around them, creating a possible discussion about security when using these cues outside the lab. On the other hand, during haptic cues, participants were clearly more aware of the surroundings, being the number of hits and the dwell time during these cues similar or superior to the baseline. In line with this, the results from SUS show that participants in terms of usability found haptic cues, in specific haptic 1P, 2W, more easy to use. When asked about what was their most and least favorite cue, all participants agreed that visual was the least favorite and haptic 1P, 1W was their most favorite. After this study, we observed that even though this was performed only by healthy people, haptic cues were not only more efficient normalizing gait, but they also showed to be more safety to use outside the lab. We aim to explain this work by performing this study on actual participants with gait disorders and by creating a wearable application that can help address gait disorders in a comfortable, usable, and safety way.